Hey guys, welcome to Crown Smart. In this video we want to show that the arbitrary intersection of topology on X is a topology on X. So here's our proof. Now for us to show that the arbitrary intersection of topology on X is a topology on X, we'll say let this T alpha such that alpha is in delta be a collection of topologies where my T alpha is a topology on X. Now if T alpha is a topology on X, then we know that the empty set is in what? T alpha, and the whole set is in T alpha, right? And we know that given any collection, let's say even a collection of O beta such that beta is in delta, we have that our O beta is in T alpha. Okay, where our O beta is in T alpha, this means that our the union of O beta comes in delta, is in this T alpha, because T alpha is a topology on X, and the finite equal to 1 to n, the finite intersection of OI is in what? T alpha, where OI is in T alpha. This is not the main thing we are doing. The main thing is to show that all this are in the arbitrary intersection of this, but already T alpha is a topology, so this is true. All this we just listed is true because T alpha is a topology. Now our target is to show that the arbitrary intersection of the topologies is also a topology on the set X. So we want to show that this is true. So the empty sets we know that the empty set is in what? In T alpha. This is true for every alpha in what? Delta. Now since empty set is in T alpha for every alpha in delta, this implies that the empty set is also in the intersection of T alpha for every alpha in what? Delta, because the empty set is in each of these T alpha, so this means that the empty set is in their intersection. Okay, now also similarly, if we have X to be in this T alpha, this also means that for every alpha in delta, so for every alpha in delta you pick, in this intersect you pick, X is in this T alpha, so this means that X is also in their what? In the arbitrary what? Intersection. So we have shown that the empty set and the whole set are in this intersection. The next thing we are going to show is the arbitrary union of the open set is in the arbitrary intersection of what? T alpha. Now let's take a collection. Let's say this is 2. Now take any collection. We're taking a collection of O beta such that beta is in delta, where O beta is in what? Remember, we want to show that the union of this is in the arbitrary intersection, so we say O beta is in what? The arbitrary intersection of what? T alpha. Okay, this is happening for every alpha beta in delta. Now let's say if O beta is in the intersection of this T alpha, if O beta is in this for every beta in delta, this implies that O beta is also in what? T alpha for every alpha in what? Delta. This means that O beta is also in what? In T alpha for every alpha in what? Delta. So this means that if O beta is in this, remember when we say if O beta is in T alpha, then what happens? Then the arbitrary union of this is in T alpha. So this means that this implies that the arbitrary union of O beta in delta is in what? T alpha, since T alpha is what? A topology on what? On X. Since T alpha is a topology on X. Now, O beta in T alpha and the union of this O beta in T alpha also implies, now since, okay, let's put it this way, since the union of O beta in T alpha, beta in this, since the union of O beta is in T alpha for every alpha in this index set, since the union of this is in this for every alpha in the index set, then this means that the union of O beta is also in the arbitrary intersection of what? T alpha. It's also in their intersection, because for every T alpha you pick, the union of this is inside every T alpha. So because the union of this is inside every T alpha, when you take their intersection, that common thing there, it means that the union of this is inside that common distance. So then the union of this is in this intersection. Okay, just like saying the union of this is in T1 or T2 or T3, T1, T2, not T1 or T2, T1, T2, T3, and then you now find the union of the intersection of T1, T2, T3. You find that the union of this, since the union is in, since this is already in T1, already in T2, already in T3, it shows that this will already be in the intersection of T1, T2, T3. So that's what it means. So we do the same thing with the finite intersection. The finite intersection says, take any finite collection, let this be a finite collection. Sorry that I'm not writing most things out because I'm trying to save time. Now take any finite collection of open sets, okay, where my OI is in the arbitrary intersection of this. My OI is this. So our target here is to show that the finite intersection of this is also in this. But OI in this T alpha, but OI in this T alpha implies that what? My OI is in what? T alpha for every what? For every alpha in what? Delta. But my OI is in T alpha. We know that T alpha is what? A topology on X. So this implies that what? This implies that the finite intersection of OI is also in what? T alpha. Since T alpha is what? A topology on X. Remember, I equal to 1 to n. So since T alpha is a topology on X, that's why we are having the finite intersection to be in what? The T alpha. Remember, OI is in this intersection, and anytime an element is in an intersection, it means an element is in, let's say if X is in A intersect B, then X is in A and X is also in B. So let's say this T alpha is T1, T2. If OI is in T1 intersect T2, it means that OI is in T1 and OI is also in T2. So that's the logic there. So OI is in T alpha. So any alpha you pick, OI is in that T alpha. So this implies that if OI is in this T alpha, and remembering the fact that T alpha is a topology on X, we now say, okay, the intersection of this is also in what? T alpha. And this also implies that since the intersection of this is in T alpha and it's happening for every alpha in delta, happening for every alpha, because if this is in T alpha, it could be in T1, it could be in T2, it could be T3, T4, T5, any value. Since this is in T alpha, it also means that this is also in the what? Also implies that this intersection I equal to 1 to n of OI is in the arbitrary what? Intersection of what? T alpha. So we have shown that the finite intersection is in the arbitrary intersection. Hence, we can now conclude that this is a what? A topology on what? X. Please, in this my video, I didn't actually give down much, just to save time, and at least with the if you can follow what I'm saying, you will get my point. And the main reason for this is just for you to understand the basics. And the truth of the matter is that if you have to go through the video over and over again, you will get more understanding of the video. Please do not forget to subscribe. God bless you. Thank you.